In this video, I'm going to explain what an ambisonic signal is, and I'm going to do this with the help of this chart. Each graphic in the chart represents one channel of the ambisonic signal, and if the channels are sorted according to the ambisonic channel number, ACN, then this represents the first channel, the second, third, fourth, fifth, and so forth. Each channel is also termed a mode of the ambisonic representation, and each row in the chart represents all modes that belong to a specific order of the representation. So the zeroth order components comprise only one mode, the first order components comprise 3 modes, the second order 5, and so forth. And if one speaks of, say, a second order ambisonic signal, then this signal comprises all modes up to and including that second order. So in this case, it will be a total of 9 modes, or equivalently 9 channels. In order to understand what signals we find in the individual channels of an ambisonic signal, we need to be aware that ambisonics encodes a sound scene relative to a given vantage point. Very much like a video camera records a scene from a specific location with a specific perspective. And here it comes. These graphics represent the directivity that a virtual microphone at the vantage point would need to have to capture a signal that is equivalent to the signal that we find in the given channel of the ambisonic signal. I'm hoping that this makes sense. So the first channel of the ambisonic signal corresponds to the output of an omnidirectional microphone at the vantage point. The second, third, and fourth channels correspond to the outputs of figure of 8 microphones at the vantage point that are oriented differently, and the higher order channels, they correspond to the output signals of virtual microphones with a more complicated directivity. Of course, in real life, it is not going to be such that the first channel will be recorded by a literal omnidirectional microphone, and the second, third, and fourth channels will not be recorded by literal figure of 8 microphones. Rather, these directivities are synthesized from the signals, from combining the signals from the microphones in an array of microphones. You may now be asking yourself, what's the point in this? What is this good for? Please keep holding on. I will explain that in the video on decoding. But before doing that, I would like to make the individual channels of an ambisonic signal more tangible by means of a concrete example. The chart at the top left illustrates the geometry of the sound scene that was encoded into ambisonics. We're looking top down onto the horizontal plane. There are 3 sound sources, a guitar, a saxophone, and a double bass. Down here, you'll find one more time the directivities that are associated to the first 4 channels of an ambisonic signal. Mind that the coordinate system in which the directivities are represented is rotated compared to the coordinate system in which the sound scene is represented. We'll have to do some mental rotation. Apologies for that. Let's pick a few example channels of that ambisonic signal. As you know, the first channel of the ambisonic signal represents the signal that would have been captured by an omnidirectional microphone. Let's listen to that. As expected, we can hear all 3 sound sources, and there was also a good amount of reverberation present upon recording. Let's now look at the second and the fourth channel. The directivity associated to the second channel happens to have a null that contains the x-axis, which is also the location where the saxophone is. So when listening to the second channel of that ambisonic signal, we have to expect that we cannot hear the direct sound from the saxophone because it is suppressed by this directivity. We can only hear the reverberation that it produces. Whereas in the fourth channel, the directivity that is associated to the fourth channel has a lobe that points into positive x-axis that points exactly at the saxophone. So when listening to this channel, we have to expect that we can hear the saxophone louder than in the other channels. I'm going to play those two back to back now so that we can appreciate the difference. The channels of this ambisonic signal that represent the higher order content will be more difficult to interpret when listening to them in isolation because of how complex the virtual directivities are that produce them. Please explore the audio examples yourself. In practice, it will be very rare that we will be wanting to listen to an individual channel of an ambisonic signal. We would rather want to listen to the decoded sound scene. And I'm going to explain in the next video what decoding is. See you there.